Hello everyone and welcome to the last day of the logarithm unit. Today we're going to look at mindful percent manipulations, which is actually a very interesting concept. The idea that if you increase at a constant percent, it's not a linear function, a constant percent. So increase at 5% over the next X amount of years, what is a total percent that it has increased? So that's what we're going to be looking at today. So let's look at the very first question. A population of wombats. If you don't know what a wombat is, I put a picture there for you. It's growing at a constant percent rate. The population on January 1st is 1,027, and a year later is 1,079. What is the yearly percent growth rate? Well, if we know it's growing at a certain percent, we're going to be looking at a geometric series here. So to find that, we can look at it as year 0 is 1,027 because we started in year 1 then is 1,079 if you want to look at it this way. And so we can always just do the geometric formula. Take the y2, 1,079, divide it by 1,027. This can give you r raised to the 1 minus 0. Well, we know it's just the first. And the answer is, I should have the answer key up here, 1.051, which we know it's growing at 105.1%, but the yearly growth rate is just 5.1%. Again, you can move the decimal place over 2 spots and then take off the 1 because the 100% just means that the original population is there. So again, percent growth we know is a geometric series or sequence, and we're looking for the R value. So what happens if they continue to grow at this rate for a decade? Remember that decade is 10 years. And we assume that the rounded percent increase from the previous one. So we know we're assuming a 5.1% increase per year, and that never changes. After 10 years, what will we have multiplied the original population by? Well, if year 1 grows by 1.051, year 2, 1.051, year 3, 1.051. And we're going to do that until we hit the last year. And so we're going to take the original population, this is the original population, and then we would multiply that by 1.051 to represent the growth for the first year, and then continue to multiply by that for 10 years. Well, another way to write that would be the original amount, and multiply by 1.051 raised 10 times, raised to the 10th. Because we multiplied 1.051 10 times due to the 10 years. Well, if we do that, then we will get $1.644, which is a total over 10 years. The wombat population increased 64.4%. So just again using your calculator there. Continuing with our wombat problem, instead of wanting to know how long it grows over 10 years, let's go backwards. Let's look at how much the wombat population grows per month. So again here we're going to look at the monthly growth rate. Well, we know that there's 12 months in a year. And so we have the growth rate of 5.1%. If we want 12 months in a year, is that going to be smaller or bigger than the yearly rate? Well, we hope it better be smaller because there's 12 months in the year, and so you're looking at a smaller growth portion. We're going to raise it to the 1/12 due to the fact that there's 12 months in the year. We're going to get 1.0042 when you do that out. And so what that's saying is that the monthly percent increase, let's try that, is 0.42%. And another way to look at that is if we had this 1.0042 as our monthly increase, if I raise that to the 12th, we should go back to 1.051. Another way to think about it, so if that did not necessarily make sense, think about it this way. We're looking for our growth rate to be x. So our growth rate we're looking at is x. If it's monthly, we know that we're going to raise it to the 12 to give us our yearly rate. We know our yearly rate's 1.051. Well, how do we get rid of an exponent? Well, we raise it to the reciprocal. Hey, what do you notice? These right there are equivalent. So just another way to think about it. If we're trying to figure out what our growth rate is, and we want it raised to the 12th, then, because there's 12 months in a year, then we can get x equal 1.0042. So again, that 1 just means it's an increase. So we're going to move the decimal spot over 2. We're going to get 4.42%. So we're done with wombats. Let's look at number 4. Let's look at a different example here. We have a population that's growing at a constant rate of 22% every 5 years. So over the 5-year span, we've grown 22%. Let's first look even right there. Let's try to find the single yearly growth rate. So I know that t to the 5th has to equal 1.22. Why do I know that? T to the 5th is the rate over the 5 years. And I want to know a single year, and therefore I just want to know t to the 1st. Well, how do I get t to the 1st? We just talked about that. We raise it to the 1/5. And when I raised t to the 5th, that was because we had over 5 years, and we raised it to the 1/5, we're going to get 1.0405. Meaning that every year, the population is increasing at a rate of 4.05%. That helps us because we now know that t equals 1.0405. If we want to find 2 years, we can then just say 1.0405 raised to the 2nd. Right? Because if it's every year, we go to 2 years. If we do that, we're going to get 1.084, meaning that we're at 8.4%. Question is, I don't want to have to find the single year every time and then raise it to that power of how many years. Like if I want to know 4 years, I don't want to have to find 1.0405 and then raise it to the 4th after that. So what we can do is take the 1.22 that we know from every 5 years, raise it to the 2/5. If I do that, you're also going to get 1.084, which is 8.4%. And so here's the idea. If we know an increase over a certain amount of years, a certain time length, we can always write it, like we could have said here, t equals 1.22 raised to the t/5, or the population. I probably should have said here, p equals that. Where t is the number of years we want to know. If it's 2 years, I just plug in 2 raised to the 2/5. 3 years, just make it 3/5. So that's another way, and a quicker way, to raise it to the 2/5, 3/5, however, t/5, where 5 is the length of increase that we were given. So let's go to look at number 5 here. So our world oil reserves are being depleted, and we're going to assume that it's a constant rate of 2% per year. So we want to determine the percent decline over the next 20 years based on this 2% yearly decline that's going to stay constant. So we're going to take the amount of decline, we'll say D equals, it's depleting, meaning we're decreasing. So we got to make sure that we're at 1 minus 0.02. So we're going to go 0.98 raised to the 20th. Pretty straightforward. We got T. So yeah, I guess I probably should have said this here. T. And then I can find D of 20, because we want to know after 20 years, 0.6676. The thing that we need to realize is, what does this 0.6676 mean? after 20 years, 66.76% of the original amount of oil is left. That's how much is left. So after 20 years, let's try to rewrite that again. 66.76% of the original oil is left. So now we want to know the percent decline. Not how much is left, but the percent decline. And here's where you're going to go 100 minus 66.76%. And it says round to the nearest percent, and so when you do that in your calculator, you get 33% decline. Okay. That's how much declined over 20 years. So key there being that you have the how much of the percent is left, and you need to subtract from 100% to figure out the decline. On to our last example of the logarithm unit. A radioactive substance half-life is the amount of time needed for half of the substance to decay. We know half is 50%. Let's say the radioactive substance, let's say we have a radioactive substance with a half-life of 20 years, meaning that it takes 20 years for the substance to decay. So we're going to look at this a few different ways. One, how most people see it is, well, if it takes 20 years to have, then to take 40 years, that's just 2 times the amount. So we know it takes 20 years to have. If it's 40 years, we're just going to raise that to the second because it's half twice. And we're going to get 0.25. So what percent of the substance is left? Is 25% is left after 40 years. What, though, we really want to find is if the half-life is 20 years, we got to find what it's decaying at per year, or what kind of expression can we even look at with this. So if we know we're halving after 20 years, we know that if t equals 20, we want this answer to be 0.5. So if t is 20, we want it to be 0.5 raised to the first. We want to divide by 20. It's that same idea of 5 years over 22% from an example above. If I plug in 20 here, 0.5 raised to the 20 divided by 20, I'm going to get 0.5. And so the idea that we have is that we know the percent decline after 20 years. I'm going to take t and divide it by 20. That's going to give us our per year rate, which we know that 0.5 raised to the 1 over 20, maybe I'll do that down here, which will give us our percent yearly decline, is 0.966. Therefore, what we can do, what percent of substance would be radioactive after 10 years, we know, going from above, goes 0.5 raised to the 10 over 20. Or after 5 years, 0.5 raised to the 5 over 20. You don't have to do the single percent and then raise it to the 10th or raise it to the 5. You can just do 0.5 raised to the 10 over 20, because we know that this is the expression for how much of the amount of substance is left per year. So the answer to this one is 70.7%, and for this one, 84.1%. So that completes logs, the logarithm unit, and I will see you in class. Enjoy.